classes on fundamentals of electrical engineering. Today we move into the fourth module, and there we discuss signals and systems. Systems happen to be basic to any type of engineering, and they are all causal. Moreover, we have both linear as also non-linear systems, wherein the linear systems happen to be just around the point of operation mostly because analysis is easier. As also computation is also much easy when we look at linear systems. We also have time invariant systems, time varying systems, etc. So this kind of theory, let me hope to try to cover as we move through the different questions in GATE examination. In the first session, we look at continuous time systems and discrete time systems as well, with focus on linear time invariant systems. So let us look at a few questions. First and foremost, let us look at some descriptions of the systems, which are very, very important, because this kind of classification helps in analysis as also in computation of what is supposedly the input that needs to be given, such that the desired output can be obtained. So let us look at the first question, where we see a system as is very descriptive of a system with an input and an output describing the system. This is, of course, in a continuous time system domain. That's the reason why xt defines the input at a particular time t. Okay, and yt defines the output at a particular time t. And what is given is that consider a system as shown below, where yt is equal to x e raised to t. Okay, so the time on which the input is defined is defined by e raised to t. Okay, or an exponential with respect to time. Okay, and hence that's going to be the output as well. Okay, so what is the kind of system? Okay, obviously the system is linear because there is a direct relationship between y and x. Okay, because e raised to t is just defining a particular time, a value for a time. Okay, so definitely it's linear. So there's no doubt that about its linearity. It's a linear system because we don't have something like x square at a point of time given by e raised to t, nor is it what can be called as a differential of x at a point of time e raised to t with respect to t squared. Okay, the dx by dt is of course linear. Okay, so this is a linear system. Okay, it is time invariant. Why? Because we have we don't have a coefficient for x with respect to time. Okay, because and e raised to t just defines a particular point of time. That's all. Okay, but on the other hand, it is not causal. Okay, so this is the most important aspect with respect to this time. So this is not an engineering system. All engineering systems happen to be causal in nature. Okay, so why do we say that it's non-causal? Because at any point of time t equal to 0, we can see that y at 0 is equal to e raised to 0 or e raised to 0 or where t equal to 0, which means that x is equal to that is y is given y at time 0 is given by x at time 1, or in other words, we are having a futuristic prediction in this, which is not possible in engineering systems. So obviously the system is linear, it is time invariant, but it is also non-causal. Okay, I hope this is clear. So let's move on to the second problem, wherein we have the system represented by the input-output relationship yt is equal to, where it's given as an integral. All differentials, all integrals are all linear in nature. But of course, there is a time zone here. The time stretches from minus infinity until up to 5t. Okay, so and you have x tau d tau as the integrand. And this is taken at t greater than 0. So what are the different options that are available? Is the system linear? Of course it's linear. Okay, but is it causal or not? It is not causal because the integration ranges from minus infinity to 5t. Okay, so 5t we'll talk about. Let's say 5 at t equal to 1, you will have time. You will have the output as y 1 or y at t equal to 1, but then the input will be guided by an integration wherein t is replaced by 5t. Okay, so 5 times 1. Okay, so it is definitely predicting a future value, so it's not causal. Okay, so linearity is of course ensured because differential operations as also integral operations happen to be linear in nature. Depending upon x tau, we might see whether it's time invariant or time varying. Okay, but it's not causal. Okay, there's no doubt about that. Let's let's go to the third question. Consider a continuous time system with input xt and output yt given by yt is equal to xt cos t. Now we have a quantity we have a coefficient for xt which is cos t, and that's dependent on time. Okay, so we have a system wherein the system is not, okay, the system defined by an input output pair yt is equal to xt cos t, xt is being the input and yt being the output. Okay, this is exactly how a system is defined. Okay, we see that we have a time varying quantity as the coefficient for xt, or this is a linear system, no doubt about it, but it is time varying. Okay, so from the different options, linear and time invariant, non-linear and time invariant, linear and time varying, so we go for option C. Okay, because there we see that that cos t varies with respect to time, and that changes the value of the output because that particular value gets multiplied by xt. Okay, so we have a time varying linear system here. Okay, let's move to the fourth problem. The input xt and output yt of a system are related as, again, the integral is okay, minus infinity t x tau cos 3 tau d tau. Okay, so now we see that the same problem that we had earlier, now it's being integrated. Okay, so automatically what comes through is that a non-time invariant system. At the same time, now we are considering the system as it gets integrated from minus infinity to t. Okay, or in other words, there is the possibility. Okay, of course, cos 3 tau tells cos 3 tau, when it becomes integrated, you will have a component of it either as a sinusoid or so as sine 3 tau or cos 3 tau. So and that is going to make it marginally unstable. Okay, and it's also possible that if this function is not going to be a finite value at minus infinity, again there's a possibility that this system is going to be unstable. Okay, so now we have talked about the new qualification for the system. The system has to be stable too, and by stability we mean that the quantity as given by the output has to be finite. Okay, so there aren't any infinite properties or any infinite quantities in the world. So stability is always talking about a real system. Okay, so let's move to the fifth question. A system with input xt and output yt is defined by the input-output relation. Okay, so this is the nature of defining a system, wherein you define the system using a pair of signals. One is the input signal, and then the output signal is a dependent signal because it depends on the input. Okay, so there are so many different aspects associated with signals and systems. What are the dependent variables? What are the independent variables? All those things come into the picture. So xt happens to be the input is always going to be an independent quantity, and output is going to be always dependent on the input. This is the nature of systems. Okay, that's why we define systems like this. Okay, so what is given here is that yt is equal to minus infinity to minus 2t x tau d tau. The system will be, okay, so we already saw that this is a non-causal system because of the minus 2t there, and of course it is time it's not time invariant, it's time varying because a coefficient t can appear in the system. Okay, and it's also unstable. Why? Because you go from minus infinity to minus 2t while integrating the system. So it's possible that on the other side, on the negative time zone, it may become unstable. So all these things are put together, and we have what is called as the D option, non-causal, time varying, unstable system. Okay. So far we have been discussing linear systems and non-linear systems, time varying systems and time invariant systems, stable systems and unstable systems, causal and non-causal systems. I suppose the four classifications at least are very clear to us. Okay, so let's move to the next section in this session itself, the impulse response. The impulse response is, again, if you give an impulse as the input to this system, which is defined by a input-output pair. If the input happens to be an impulse and you get a response, that you call that as an impulse response. Okay, impulse response is always defined in time. Okay, so though you use Laplace transform for defining the input as well, for defining the input as also the output in S domain. Finally, you always represent the impulse response in time zone. That's why it's given that the impulse response GT of a system G is as shown in figure. What is the maximum value attained by the impulse response of two cascaded blocks of G as shown in the figure? Okay, so what do we have here? We have the first figure which explains the response of the block G. Okay, so what does it do? If you give it an impulse, it creates what is called as a small pulse out of it, and the pulse has a width of 1 and the height of 1. Okay, the magnitude is equal to 1, and the pulse with respect to time is going to be of width equal to 1. Okay, so 1 time unit. Okay, so and that of course you can convert into a Laplace transform because when we are having cascaded systems, the Laplace transform of the cascaded systems can be multiplied together. So this is an important input that we will be using in signal systems all through. Okay, so what is the Laplace transform of such a small pulse? Okay, so it's given by 1 by S. Why? Because it's actually the pulse is created out of two step inputs, unit step inputs. One is which starts off at t equal to 0. The other is of course which of course starts off at t equal to 1, but then it deducts from the earlier version. So we are left with the pulse. Okay, or in other words, a window is obtained out of ut minus 1. Okay, in this case. Okay, so ut minus 1 into is multiplied by 1 is going to be the time nature of the waveform that we have in the form of a pulse. Okay, so if you take its Laplace transform, it's going to be 1 by S into 1 minus e raised to minus S. Okay, so now we are having two cascaded ones, so you multiply them together. So you see that it's the same as equal to 1 by S square into 1 plus e raised to minus 2s minus 2 e raised to minus s. Okay, so of course we want to know the maximum value that it can attain, and this can be easily converted into a diagrammatic picture in your mind. Okay, which will give you the answer. Okay, what happens at t equal to 0? Okay, when you're trying to what happens at s is equal to 0 when you're trying to draw. Okay, or okay, what happens at t equal to 0 when you're trying to draw the Laplace inverse of this? What happens? We get the Laplace inverse of 1 by s square as t. So we see that with the slope 1, we have a time dependent or a linear kind of movement for the output. Okay, so that's equal to t. Okay, and then so it goes from 0 to 1 in time zone as also in amplitude zone because the slope is equal to 1. Okay, then you are having 1 by s square into e raised to, then at t equal to 1, what happens is that you are going to have minus 2 e raised to minus s by s square being Laplace invertible to again minus 2t. Okay, but of course it starts off at t equal to minus 1. So and what does minus 2 mean? It means that there's a negative slope, and moreover it's very steep. Okay, and that's the reason why in the sketch given we have shown a line which is having negative slope, and it's also steep. Okay, so it's passing through, and the total height is going to be 2, and and this is through 1 time unit. Okay, so we see. Okay, then at t equal to 2 we arrive at the third quantity in the Laplace transform. What is that? 1 by s square into e raised to minus 2s. What does it mean? It means that again you are having a positive slope of 1. Okay, so it's and so the minus 2 slope is now offset a little by the positive slope, and then it continues to go further. Okay, so and then with that it stops. Okay, so we see that we are having what is called as a quantity for the output from the two cascaded blocks, which goes until up to 1, and then it is always going to be negative in nature. Okay, or in other words, we see that we are having the maximum value is equal to 1. Okay, as it is, the given values are 2 by 3, 3 by 4, 4 by 5, and 1. So 1 happens to be the best of the lot, and it's the only answer that's possible. Okay, so let's move to the 7th question. What is given here is that consider an LTI system with impulse response ht equal to e raised to minus 5t ut. As we saw in the previous example, when an impulse is given, there is a response, and it starts off only at t equal to 0. That's the reason why the right side window is kept open by using the expression ut. Okay, and e raised to minus 5t tells us that it's an exponentially decaying kind of response. Okay, and it's an impulse response, so the input is going to be a Dirac delta function or a delta t. Okay. The output of the system is yt is equal to e raised to minus 3t ut minus e raised to minus 5t ut. Then the input xt is given by. Of course, there are plenty of methods for doing the problems, but my mission is to give you the easiest as I see them. And what and of course with the concepts entered within. And so here we see that there is a response. Okay, any response has two components. One is what is initiated by the input. Okay, so even if the input is not there, sometimes there is a response because of the internal initial conditions, or what are called as the internal conditions. Okay, or what is called as the space of the state of the space of the system. So all these things are referring to the same energized situation that is there within the system, or the internal energy that is there for the system. Okay, due to something that has already come to it. Okay, just like the residual magnetism and similar situations. Okay, so here we are having the output dependent on not only the input but also on the system, and the system has already given its outcome or its influence on the output as a component as e raised to minus 5t. Okay, minus e raised to minus 5t. Okay, the other component is e raised to minus 3t. So the input initiated one is going to be e raised to minus 3t ut. Or in other words, we are talking about two responses. One is what is called as a zero state response, wherein the input takes over. Okay, or e raised to minus 3t, or its components take over. Okay, and there is also what is called as the zero input response. That is when there is no input. Again, there is a response, and that is where the e raised to minus the state comes in, or e raised to minus 5t ut of the impulse response comes in. Okay, so we are so we see that the zero state response, or the one with which is initiated only by the input is a function of e raised to minus 3t. And from amongst the four answers, we notice that only A and B have e raised to minus 3t ut. Okay, one is e raised to minus 3t ut, and the other is 2 into e raised to minus 3t ut. So which is more suitable? So we realize that when you are having two components joined together in a convolution, like for instance hs xs, so hs is going to be 1 by s plus 5 and xs is going to be 1 plus or something by s plus 3 because of e raised to minus 3t. In that case, the residue of e raised to of s plus 3 will have to be positive. Okay, and it will also have to compensate for the difference between 5 and 3, because these are the two poles of the system. So 5 minus 3 is equal to 2. So 2 into e raised to minus 3t ut is always going to be the natural solution, which you can do which you can find out without going through the complete solution using partial components. Okay, so this is the suggestion that I have for you for solving these kinds of problems, which we will be encountering again in the next session. Okay, so let's look at the last problem in this session, which is again an impulse response of a system ht is equal to t ut. Okay, so here we have a difference in the sense that earlier it was exponential, now it's a ramp kind of response initiated at t equal to 0 or on the right side of the time axis. Okay, for an input ut minus 1. So now the input is different other than what was given earlier, and other than what happened when we gave an impulse, it is going to be ut minus 1. So what is ut minus 1? It is a step input which is delayed to t equal to 1, or t minus 1 equal to 0, or t equal to 1. So a delayed input will give rise to what is called as an additional Laplace transform component as given by e raised to minus s. The time component here is going to be 1. Okay, so this is something that we remember. And another point that needs to be remembered is that if the impulse generates a response as given by t ut, then its integration, that is its integrated, that the impulse's integrated version, which is the step input or unit step input, will result in an integrated version for the response in Laplace domain as well. Or in other words, you can take the Laplace transform of TUT, that gives you 1 by s square. You can take its integration, which is going to give you 1 by s cube, and then you can go back to time domain. Okay, so this is what is suggested here. So if you go back to time domain, it becomes the same as equal to to get the response for the step response is what we are doing right now. We see that 1 by s cube has a Laplace inverse as given by t square by 2. But then we have not yet taken care of the delayed input. So to take care of the delayed input, we have to remember that now there's an offset as given by e raised to minus s. Okay, so e raised to minus s is Laplace inverse into replacing every t by t minus 1. Okay, so we are having t square by 2 as equal to t minus 1 whole square by 2, and at the same time, the fact that it is initiated only at t equal to 1, you have to add the component of ut minus 1. So option C is the best answer. I suppose by now some of the classifications as to how you wean out the calculations or how you distinguish them, as also the impulse response components are clear to you. The remainder of the problems that have come in GATE examination in impulse responses, as also some of the additions will be discussed in the next section. Okay, thank you.